In this work example, we're doing a little bit of rocket science here, and we're going to start with state Newton's second law of motion. If you have memorized the Newton's second law of motion as F equals ma, then you need to remind yourself this is AICE physics, okay? Where we don't just consider a special case of the more general truth, F equals the rate of change of momentum. Force is the rate of change of momentum. That's a good way to state Newton's second law. When mass is constant, force equals mass times acceleration. Okay, so mass times final velocity minus mass times initial velocity over the change in time is a way to sort of expand this. This is final momentum minus initial momentum. And if the mass is constant, then we can factor it out and get the familiar rate of change of velocity, which is acceleration. So we have to note that this is a special case, all right, when mass is constant. But force is the rate of change of momentum, and that's a good way to think about Newton's second law of motion. Okay? It's a better way to think about it. So think about it the AICE physics way, because this is AICE physics. A toy rocket consists of a container of water and compressed air, as shown in figure 3.1, and as will be demonstrated with our fun laboratory activity. It's not going to be like an experiment with a capital E, because we're not going to, like, you know, vary one quantity against another. We're just going to go out and launch some rockets and have fun. This is going to be an activity to just demonstrate this. It will be great fun. It says water is pushed vertically downwards through a nozzle by the compressed air. The rocket moves vertically upwards. The nozzle has a circular cross-section of radius 7.5 millimeters. The density of the water is 1,000 kilograms per cubic meter. That's the second time we've seen the density of water today. Assume that the water leaving the nozzle has the shape of a cylinder of radius 7.55 millimeters and has a constant speed of 13 meters per second relative to the rocket. Show that the mass of water leaving the nozzle in the first 0.2 seconds after the rocket launch is 0.46 kilograms. Okay. So earlier today, in astronomy, we were talking about density and how density is mass per volume. And oftentimes we're going to use a known density to calculate the mass of something whose volume we can also calculate. So we're really going to, show that the mass of water, and say, well, what equation, what idea here even contains mass in it? Maybe it's a weight or something like that, but it's actually, okay, kilograms of mass, right? So a density has sort of mass embedded within it. So we'll rewrite this as mass equal to volume times density. I like to write out the word volume, this V for velocity, right? Like this V up here is velocity, write out volume. All right, a cylinder. Does anybody know how to calculate the volume of a cylinder? If you don't, it's okay, because you can, bless you, it has a circular cross section. And this is the way to think about volume in physics. The two-dimensional area, the area of the base, times the third dimension. That third dimension is sometimes called H for height, or T for thickness, or D for depth. Lots of other variables that we could consider that, but it's like length times width times height, right? We know that's how to calculate volume. So length times width is an area times height. The thickness of like a coin, the depth of the ocean. So it's like whatever the 2D area is times whatever they're calling the third dimension. Here, we got the radius of our cylinder, and we know it's traveling at 13 meters per second, right? The water is traveling at 13 meters per second. Let something go 13 meters per second for 0.2 seconds, and how high will it be? You see how we have enough information to calculate this. There's a cylinder of water that's being ejected out of this nozzle here. And the area is going to be the area of a circle. So the volume here is going to be pi times r, 7.5 millimeters, pi r squared times height. All right, so the 2D area is our pi r squared. The third dimension is the height. And the height is going to be able to be calculated with it's a displacement, right? So height is like a vertical displacement. So there is a vertical component of velocity. The velocity is 13 meters per second, and we're allowing that to travel for 0.2 seconds. So that's kind of tricky, right? Because they give you the speed, they say, in the first 0.2 seconds, show that the mass of water leaving the nozzle, well, it's leaving at a speed of 13 meters per second, but it only goes for 0.2 of a second, right? So how many total meters is that? What's 13 times 0.2? 2.6 meters. All right, seconds cancel, and then meters, good. Meters squared times meters, it's cubic meters, which are units of volume, right? So this gives me the volume. And if I was so caught up in that calculation, like, oh, the tricky thing is how to calculate the volume, oftentimes students are just going to calculate that and record it as the mass. And I was like, oh, that's just the volume though, right? Like, don't forget, the units are a great way to keep track of it. What do I have when I multiply meters times meters squared? It's just cubic meters. Then you remind yourself, oh yeah, those are the units of volume. I got to multiply it by a density in order to convert volume into mass, right? So the density of water is 1,000 kilograms per cubic meter. Remember that M is different than that M, right? This is M for mass, that's M for meters. And you got to just be able to look at it in the context there. So now our cubic meters are going to cancel. I don't want to cancel this because I need to remember to square the number, but I get kilograms of mass, right? All the units cancel out to give me what I would expect. All right, so everybody with a calculator maybe still has 2.6 meters there. Let's multiply it by 7.5 by 10 raised to the -3. I want to square that. And then multiply it by pi. Looking at my calculator here. Okay, I found a pi button. Times pi times 1,000. All right, anybody out there looking at something that's close to 0.46? It's nice when they say show that the mass is this, because then it's like, okay, if I didn't show it, then I would find my mistake right away. So you get 0.459, 457, and so on kilograms, which is indeed about 0.46 kilos. All right, so always kind of like show the calculator value a little bit more precise and say, okay, yeah, and is about equal to the thing that I said it should be. All right, so nice little reminder that we can calculate mass in terms of density, and that volume in general is a 2D area, the area of the base times the third dimension. Very useful way to think about it. I want to calculate the change in the momentum of the mass of water in B1. So we have 0.46 kilograms due to leaving the nozzle. All right, change in momentum. Jump that. Change in momentum is final minus initial. The initial momentum is 0, right? Because it starts out at rest due to leaving the nozzle. So we just calculate the final momentum. I think we're done, right? Change in momentum is whatever this is minus 0. It had 0 momentum to start with. It was at rest. So the final momentum is just mass times velocity. Okay, 3 marks for both of these here. So the mass is just 0.46 kilograms, right? We showed that, and the velocity was 13 meters per second. A kilogram meter per second is the same thing as a Newton second. So I still have the 0.45945 and so on in my calculator. I'll just keep that there, multiply by 13. I get 5.97. So 6. The force exerted on this mass of water by the rocket. So remember what we started with, Newton's second law. Force is the rate of change of momentum. So I think we can just take the 6 Newton seconds of momentum change divided by the 0.2 seconds, right? So this is kilogram meters per second. So kilogram meter per second squared is a Newton. You may recall the base units there. And so you just do that 5.97 or the rounds up to 6 divided by 0.2 equals, you get 29.86. In the calculator, which is nicely rounded to 30 newtons of force. It's just sort of trusting those definitions, right? Like force is the rate of change of momentum. We calculated change in momentum. They gave us the delta t, right? The time over which we're considering. So we just trust it, calculate it. State and explain how Newton's third law applies to the movement of the rocket by the water. Okay. Newton's third law says that forces exist in pairs, equal in magnitude, opposite in direction. So the thrust force, right, which is the force of the sort of the water crashing into the launch pad and into the earth, has an equal and opposite force, right? The downward force of the fuel hitting the launch pad has an equal and opposite upward force that we call thrust. So the thrust is the force that propels it upwards, right? The force of the water crashing into the launch pad, that's the equal and opposite force there. So it's a contact force, right? It's actually changing its momentum, right, as it crashes into the ground. So Newton's third law applies here to the movement of the rocket because there's an equal and opposite force to the force that the sort of Earth exerts to the water exerts on the Earth, and that's what generates thrust. So, kind of put that in your own words, check the language of the mark scheme and see if that sort of agrees with it. We'll queue up the mark scheme at the end here at the suggestion of one of our viewers. Always good to check the mark scheme. The container has a mass of 0.4 kilograms. The initial mass of water before the rocket is launched is 0.7. The mass of the compressed air in the rocket is negligible. Assume that the resistive force on the rocket due to its motion is negligible. For the rocket, at a time of 0.2 seconds after launching, show that its total mass is 0.64. So if you just read through all of that, that should be pretty straightforward. It's like saying it had a total mass of 0.7 plus 0.4, right? So that's 1.1 kilograms initial. And after 0.2 seconds, we've already calculated that how much water was ejected, 0.46 kilograms, right? So like we lost 0.46 kilograms of our original 1.1. And so my mental math should be good enough to just be like, oh yeah, that's equal there, but I have to type it in the calculator, just prove it to myself. Yep, that's 0.64. Because if it wasn't that, it's like, oh, did I miss something here? Like, okay, yeah, it's pretty straightforward there. The total mass is 0.64 for the rocket at a time. The rocket still has this mass, right? It still has its container plus a little bit of water still inside it. Not all the water has left yet, otherwise it would just be equal to this. Calculate its acceleration. So here's where it's really easy to make a mistake, okay? You can go, I'm solving for acceleration. I just did something with mass here, F equals ma. And it's tempting to just multiply, to take the force that we've previously calculated, 30 newtons, right? We know that that's the force. And again, it's an equal and opposite force, like the force of the water pushing down on the launch pad has an equal and opposite force of the launch pad and Earth pushing back up on the rocket. And the up force is called thrust, which makes it move. Tempting to just go 30 equals 0.64 times A. But we have to remember that this equation is really the net force. The sum of the forces equals mass times acceleration. So we've got a rocket here. For a rocket, let's just approximate it as this point in space. And the rocket has mass, has a total mass of 0.64 kilograms. And if it has mass, we usually label the mass up here, like make it a box with the mass in here. The force acting down on the mass is the weight, mg. So it's the 0.64 kilos times 9.81 newtons per kilogram. There's already a weight force acting down. The acceleration is due to the net upward force, the thrust that's propelling it upwards, right? And so 30 is not the correct value to substitute in here, right? It's not the net force, okay? That's the force produced by the water, right? The force exerted on this mass of water by the rocket. So the rocket exerts that force goes down and gives it acceleration up. We got to subtract away the weight from it, right? So we have 30 newtons of equal and opposite thrust force. So we've got 0.64 kilograms times 9.81 newtons per kilogram. We've got 6.2 6.3 or so newtons acting down. So we need to first sum the forces or realize that mass times acceleration solves for the net force and not there's a down force in addition to the upwards force there. So the left side of this is 30 minus 6.27. So that gives 23.72 divided by 0.64, and you get an acceleration of 37 meters per second squared, which is your answer there. This is one g-force. So the way that I had solved it previously, like forgetting this, if you just do 30 equals 0.64 times A, 30 divided by 0.64, you get 47. And you go, okay, yeah, well, it's 46.8. You say, okay, there's one g-force added to that if you forget to subtract away the weight, which is the force you're feeling right now. Like everybody on Earth is feeling one g-force, right? One force of gravity, right? And so that's why you can kind of compare the answers like that. All right, so don't forget to sum the forces to subtract away sort of the weight. You get a final answer of 37. Now, as promised, we're going to change this. On S. Shout out to cienotes.com for all your previous ACE paper needs, including the mark sheet. So now we're going to look at question number 3 there. Let's see how well we did. The resultant force is proportional or equal to the rate of change in momentum. See how they're defining it in terms of momentum. We got density as mass per volume. So the volume is all that. And the mass is 0.46. So they show it the same way. We've got 6 Newton seconds, just taking mass times velocity. The change in momentum is just the final momentum. And then the change in momentum over the change in time gives the force. That's what we defined up here. So far, so good. The force on water by the rocket or the nozzle is equal to the force on the rocket or nozzle by the water. So it's always 2 objects interacting. The forces are equal, but in the opposite direction. So they've got that sort of key idea there. So what are the 2 objects that are interacting? And make sure that you state that the forces are equal, but in the opposite direction. The mass agrees with our calculation, calculating the total mass minus the mass that you're able to show sort of back here, right? 0.46. So that's all the rest of the mass. And then look at the 2 ways that they've approached the final calculation. You could have taken 30 minus 0.64 times 9.81. That's what we did, right? We calculated the weight and we said, well, this weight opposes the thrust force divided by the mass. But you could have done the calculation that we, originally did, was take the total, the thrust force divided by the mass 0.64 and then subtract away 1 g-force. Okay, and so that gives you to the same answer right here. Like you solve it, how many g-forces? Oh, minus the weight, that's 1 g-force of weight I got to account for, right? So only 37 instead of 47. If you divide 37 by 9.81, you're converting it into units called g-forces, right? Like 1 g-force is the acceleration due to gravity. So there's 3.77 g-forces that the imaginary mini astronaut aboard that water rocket would be experiencing. All right, I'm glad we could clean that one up.